Hi and welcome to day 26 of Just Start Programming, the Rust programming language. We are now moving on to advanced topics in Rust. And if you have just started watching my video, it would be great if you could start from day 1 if you are totally new to Rust or if you have forgotten some concepts. One of my purpose in doing this video is also for me having it recorded so that I can also backtrack if I forget certain concepts. So today we'll try to cover Fearless Concurrency. We won't be able to finish all chapter of the Rust book, but we will take this step by step. So join me, learning it live in one take, no shortcuts, no secrets. Let's just start programming. Right, so here we are. Yesterday, we just scanned through reference cycles and how it can leak memory. So our focus for today is mainly on this topic. As yesterday we spent a lot of time analyzing ref cell. Let's scan quickly. Okay. I think we have done this also, if I'm not wrong. Let me check the code. Yep. So here it is. How about yeah, so I think we have done this yesterday. Okay. Let's start once again with the reference cycles, which it says here it can leak memory. Let's read through. Rust memory safety guarantees make it difficult, but not impossible, to accidentally create memory that is never cleaned up, known as memory leak. Preventing memory leaks entirely is not one of Rust guarantees, meaning memory leaks are memory safe in Rust. We can see that Rust allows memory leaks by using RC and refcell. It's possible to create references where items refer to each other in a cycle. References where items refer to each other in a cycle. This creates memory leaks because the reference count of each item in the cycle will never reach 0, and the values will never be dropped. Creating reference cycle. Let's look at how a reference cycle might happen and how to prevent it. Starting with the definition of list, enum, and tail. Tail is something new. Method in listing 15-25. Oh, it's a function. Okay. So here we're still using list, cons and nil, cell, ref cell, and RC. Here I32, and then you're using ref cell enclosing RC list. Then in list you have the function tail, takes reference to itself, it returns option with a reference to reference cell enclosing reference count, which is list. match self cons item sum. Okay, option should return sum or none. Okay, let's read this part and see what exactly was meant by this code. We are using another variation of the list definition from 15-5. The second element in the cons variant is now ref cell RC list. Let's check the code previously. How was it? Oh, it's the other way around. Here we have ref cell and then RC. Okay. Here it is still I32 and we have ref cell RC list. Okay. Meaning that instead of having the ability to modify I32, so we're not modifying I32 anymore, values we did in this thing, 15-24, we want to modify the list value. A cons variant is pointing to. We're also adding a tail method to make it convenient for us to access the second item if we have a cons variant. So it's a tail. So it says here, we are also adding a tail method to make it convenient for us to access the second item if we have cons variant. Okay, so match cons sum item. Meaning, I don't understand it yet, but let's see. Access the second item if we have the cons variant for the second item. If you have cons variant, okay, then you're accessing the item. Okay, in listing 15-26, this one, we're adding a main function that uses the definition listing 15-25. This code creates a list in A and a list in B that points to the list in A. Okay, we have A, RC new, const, this is still I32 basing on this one, ref cell new, okay, because now we have ref cell, we are enclosing RC, RC new nil. Okay, so A starts with 5 and the next one is nil. A initial RC count should be 1. A next item, A tail. Okay, so A tail, so the self, A tail. So it is supposed to return option. Okay, match self cons item nil equals to none. Nil to none. Okay. Does it say here? List in A and list in B points to list in A. Okay. So list in B. So B, you have new cons 10, which is I32, and then ref cell new RC clone %A. So here we are incrementing reference count. So now it should be 2. ARC count after B creation. B initial RC count. B next item, B tail. Okay. If some link A tail returns some if it has something. Okay, dereferencing link, because link is what is it returning? Some reference cell RC. So it should be borrow mat. Okay, this one is for this. Then borrow mat is for this. RC clone. So there's another RC clone here for B. Print line. B RC count after changing A. B RC count after changing A. What's the value here? A RC count after changing A. 1, this is 1, this should be B. Wait, B points to A, so 1, B10. B is 2. Changing A. A is A 1, 2. 2, 2. Okay, that's my assumption. Maybe my guess is wrong. Okay, we create RC list instance holding a list. Value in variable A with an initial list of 5, then nil. When we then create an RC list instance holding another list. RC list holding another list value in variable B. That contains the value 10. Okay. Contains the value 10 and points to the list in A. Points to the list in A. Okay. We modify A so it points to B instead of nil. Okay. So this is the key part, because initially A points to 5 and then nil. So here it is modified to be A points to B instead of nil. So now it's like from here it points to B and B points to A. Okay, creating a cycle. We do this by using the tail method. It's the tail method. B A tail. Is it this one or is it this one? To get a reference to the ref cell RC list in A. By using the tail method to get a reference to our ref cell in A, which we put in the variable link. Then we use the borrow mat method on ref cell. Yeah, so borrow mat. Okay, because this is A, so borrow mat a ref cell. Yeah, borrow mat is for the ref cell. ref cell RC list. Okay, so it's the entire ref cell RC list. To change the value inside from an RC list that holds a nil value to RC list in B. Okay. So it's like it's taking this part from tail. Tail will be returning this part and then pointing it to RC clone B. Okay. When we run this code, keeping the last print line commented out for the moment, we'll get this output. A initial RC count equals to 1. Let's see, A initial equals to 1. Yeah, it's 1 here. A next item, A tail. So reference nil, so it's nil. And then here, A RC count after B creation, so this becomes 2. Yeah, correct. B initial RC count equals to 1. B initial RC count equals to 1, so because we have just started with B. Then B next item equals some ref cell value cons 5 ref cell nil. Okay, so in this case, B is already pointing to A. Okay. B next item equals B next item equals B tail. B tail is 10 pointing to A, which is 5 pointing to nil. Okay. But why is it 5 reference nil? Some ref cell value cons 5. Okay. B next item. B next item. So if this is B tail, okay, so tail is this one. Okay, so it's correct. Tail is this one, so that would mean it's 5 then nil. 5 reference cell value nil. Okay. B RC count after changing A equals to 2. Yeah. B RC count after changing A equals to 2 because here it's already 1 referencing A, so it becomes 2. A RC count after changing A, so A is 1, this is A is 1, this is 1, this is 2. Then this should be 3. No. A RC count after changing A equals to 2. A RC count after changing A equals to 2. Why? Let's check again. A initial RC count is 1. Okay, A initial RC count is 1. A RC count after B creation becomes 2. Okay. A after B creation becomes 2. So it's already 2 here. Why is it that A RC count after changing A is still... Wait. 2. Okay. So it's still 2. Yeah. Still 2 because here we did not do anything to do a reference count somewhere, but in this case it's Let's link a tail. Okay, a tail. Actually here A is pointing to B. A is pointing to B. A reference. Reference count. No. Reference count for B. Okay, so A is still 2 in this case. Okay. The reference count of the RC list instance in both A and B is 2 after we change the list in A to point to B. Okay, so here's the diagram. At the end of main, Rust drops the variable B, which decreases the reference count of B instance from 2 to 1. The end of main. The memory that RC list has on the heap won't be dropped at this point because its reference count is 1 and not 0. Then Rust drops A, which decreases the reference count of the A RC list instance from 2 to 1. This instance memory can't be dropped either because the other RC list instance still refers to it. The memory allocated to the list will remain uncollected forever. To visualize this reference cycle, we've created the diagram. Okay, so initially A is pointing to I32 5 and nil. Then B is pointing to 10, and then it points to A. But A now points to B. A points to B. Yeah, A tail points to B. A points to B. If you uncomment the last print line and run the program, Rust will try to print this cycle with A pointing to B, pointing to A, and so forth until it overflows the stack. Let's buffer overflow. Compared to a real-world program, the consequences of creating a reference cycle in this example aren't very dire. Right after we create the reference cycle, the program ends. However, if a more complex program allocated lots of memory in a cycle and held onto it for a very long time, the program would use more memory than it needs and might overwhelm the system, causing it to run out of available memory. Creating the reference cycles is not easily done, but it's not impossible either. If you have ref cell T values that contain RCT, ref cell T that contains RCT values, or similar nested combinations of types with interior mutability and reference counting, you must ensure that you don't create cycles. You can't rely on Rust to catch them. Creating a reference cycle would be a logic bug in your program that you should use automated test, code reviews, and other software development practices to minimize. Another solution for avoiding reference cycle is reorganizing your data structures so that some references express ownership and some references don't. As a result, you can have cycles made up of some ownership relationships and some non-ownership relationships, and only the ownership relationships affect whether or not a value can be dropped. In listing 15-25, we always want const variant to own their list, so reorganizing the data structure isn't possible. Let's look at an example using graphs made up of parent node and child node to see when non-ownership relationships are an appropriate way to prevent reference cycles. Okay, so for graphs made up of parent nodes and child nodes, Preventing reference cycles using weak T. So far, we've demonstrated that calling RC clone increases the strong count. RCT instance and RCT of an RCT instance. And an RCT instance is only cleaned up if its strong count is 0. We can also create a weak reference to the value within RCT instance by calling RC downgrade and passing a weak reference to the value within RCT instance by passing reference to the RCT. Strong references are how you can share ownership of RCT instance. Weak references don't express an ownership relationship, and their count doesn't affect when RCT instance is cleaned up. They won't cause a reference cycle because any cycle involving some weak references will be broken once strong reference count of values involved is 0. Okay, so they won't cause a reference cycle because any cycle involving some weak references will be broken once a strong reference count of values involved is 0. When you call RC downgrade, you get a smart pointer of type weak. Okay, so this is very important concept. RC downgrade. You get a smart pointer of type weak. Instead of increasing strong count in RCT instance by 1, calling RC downgrade increases the weak count by 1. So that's why you have strong count and here you have weak count. The RCT type uses weak count to keep track of how many weak references exist, similar to strong count. The difference is the weak count doesn't need to be 0 for the RCT instance to be cleaned up. So it doesn't have to be 0. So it can be used for cycles. Yeah. So it can be cleaned up even if weak count is 1. Maybe there's an example here later. Okay, because a value that weak T references might have been dropped, to do anything with the value that the weak T is pointing to, you must make sure the value still exists. Do this by calling the upgrade method on a weak T instance. But RC downgrade makes it weak. But from weak T, by calling the upgrade in method on weak T instance, which will return an option RCT, you get a result of some RCT value has not been dropped yet, and a result of none RCT value has been dropped. Because upgrade returns option RCT, RUST will ensure that some case and non-case are handled, and there won't be any invalid pointer. As an example, rather than using a list whose items know only about the next item, we'll create a tree whose items know about their children items and their parent items. Creating a tree data structure, a node with child nodes. Okay, so creating a tree data structure. To start, we'll build a tree with nodes that know about their child nodes. We create a struct named node that holds its own I32 value as well as a reference to its children nodes values. Reference to vector of RC node. Okay, let's copy this one. Let's put that in our code. Yes. We will just insert here. Okay, we want a node to own its children. And we want to share that ownership with variables so we can access node in the tree directly. To do this, we define vector t items to be values of type RC node. We also want to modify which nodes are children of another node. So we have ref cell t in children around the vector RC node. So it's describing this one. Ref cell t in children around vector RC node. Next, we'll use our struct definition and create one node instance named leaf with a value 3 and no children, and another instance named branch with value 5 and leaf as one of its children. Okay, let's copy this. So there's a leaf, which is an RC node. New node value 3 and children is a reference new to a vector. Then branch, RC node value 5, children is ref cell new to a vector RC clone leaf. So what does it say here? We clone RC node in leaf and store that in branch, meaning the node in the leaf now has two owners. It has two owners, leaf and branch, leaf and branch. Right. We clone RC node in leaf, I think it's referring to this one, and store that in branch, meaning the node in leaf has two owners. Leaf and branch. The node in leaf now has two owners, leaf and branch. Leaf and branch. Where are we? Okay, here. Leaf and branch. We can get from branch to leaf through branch the children. Branch to leaf through branch the children, but there's no way to get from leaf to branch. The reason is that leaf has no reference to branch and doesn't know they're related. You want leaf to know that branch is its parent. We'll do that next. Okay. To make the child node aware of its parent, we need to add a parent field. Okay, because now, until now, it's only children. Where were we? Okay. To make the child node aware of its parent, we need to add a parent field to our node. Struct definition. The trouble is in deciding what the type of parent should be. We know it can't contain an RCT because that would create a reference cycle with leaf.parent pointing to branch and branch children pointing to leaf. Yes, cannot use this, which would cause their strong count values to never be 0. So RCT is a reference counter, so it has always something to do with strong count. Thinking about the relationships another way, a parent node should own its children. A parent node should own its children. If a parent node is dropped, its child node should be dropped as well. However, a child should not own its parent. If we drop the child node, the parent should exist. This is a case for weak references. Okay. Usually, a parent node should own its children. If a parent node is dropped, its child node should be dropped as well. However, a child should not own its parent. If we drop a child, the parent should still exist. Okay. This is a case for weak references. So instead of RCT, we'll make the type of parent use weak. Specifically, ref cell weak node. Oh, okay, RCT. Now our node structure definition looks like this. Let's copy this one. So parent, a node pointing to its parent is weak. Okay. Children, okay, a node pointing to its children. This one is strong count. But this one will definitely complain. Oops. And then let's copy this part. Okay, so weak was not added, so we need to add weak. RC weak. Do the analysis. Yeah, so the change is over here. Okay, so leaf now is having a value 3. Its parent, you'll have a weak reference. I know, weak count. Parent is new. Children, ref cell, vector. Okay. Print leaf parent, borrow. Why is it borrow? Why is it borrow again? Why not borrow mat? Borrow, okay, so it's not mutable but immutable. Okay, borrow, upgrade. It is upgrade all about. Is it a function? Yeah, it's a function. Is it a function of ref cell? Or if it's okay, I think it's a borrow will return weak. So upgrade is for weak. Okay. Let branch RC node 5 ref cell with new most the same. Then children vector RC clone. Okay, so RC clone leaf. So branch its children is the leaf. Okay, branch children is the leaf. Leaf parent, who's parent? It's the leaf. Parent is this one, borrow what weak, RC downgrade branch. Okay, because parent is weak, what does it do if you have RC downgrade branch? Borrow, upgrade. This is to check leaf. If bit lost. Let's see the description instead. Creating the leaf node looks similar to 15-27. With the exception of the parent field, leaf. Okay. Parent field. We create a new empty weak node. Reference instance. At this point, when we try to get a reference to the parent of leaf by using upgrade method, upgrade here, we get a non-value. We see this in the output in the first print line. Non-value because parent points to weak new. When we create the branch node, it will also have a new weak node. Create the branch node, new weak node. So the same. Reference instant. At this point, we try to get a reference to the parent of the leaf by using upgrade. We get a reference to the parent of the leaf by using upgrade. We get the reference to the parent of leaf by using upgrade. Leaf parent is this one, borrow represent weak, and upgrade. We get a non-value. Okay. When you create a branch node, it will also have new weak node reference in the parent field because branch doesn't have a parent node. We still have leaf as one of the children of branch. Once we have the node instance in branch, we can modify leaf to give it weak node references to its parent. We use the borrow method on ref cell. Borrow mat. In the parent field of leaf, and then we use RC downgrade function to create a weak node. Reference to the branch from RC node in branch. As it downgraded. Okay. Downgrade function to create a weak node. So downgrade function to create a weak node. So this becomes a weak node. In the parent field of leaf, there we use function very weak node. Reference to branch from RC node in branch. Okay, downgraded function to create a weak node reference to branch from RC node in branch. When you print the parent leaf again, this time we'll get some variant holding branch. Now leaf can access its parent. When we print leaf, we also avoid the cycle that eventually ended in Stack Overflow like we had listed. The week node reference are printed as week. Some week. 3 paragraphs a week. Okay, the lack of infinite output indicates that this code didn't create a reference cycle. You can also tell this by looking at the values you get from calling strong count and weak count. Visualizing changes to strong count and weak count. Okay. Let's look at how the strong count and weak count values of RC node instances change by creating a new inner scope and moving the creation of branch into that scope. By doing so, we can see what happens when branch is created and then dropped when it's out of scope. The modifications are shown in 15-20. So it was modified. Oh, this one is quite long. Let's copy. Okay, let's read the explanation. After leaf is created, its RC node has strong count of 1 and a weak count of 0. Okay. Leaf strong count of 1 and a weak count of 0. No, strong count of strong count of 1 and a weak count of 0. The inner scope, we create, branch, and associate it with leaf. So here's the inner scope, created a branch and associated with leaf. Star leaf parent. So the leaf whose parent is this one. Parent. So we borrow mat is equals to RC downgrade at branch. Okay, RC downgrade is to create a weak reference count. So the reference count to branch is downgraded. Okay, this is 1, then downgraded. Let's see. Print line branch strong branch. Strong branch is 1. Weak count, because it's downgraded, so 1 1. Branch strong 1, weak 1. Where is it? It's not shown. Maybe we can run the code. Okay, leaf strong 1, weak 0. Branch strong 1 1. Okay, 1 1. We're correct. 1 1. Weak count was incremented to 1 because of the downgrade. Then here, leaf strong count, leaf was 1 here. No, 1 2. So leaf is it? Okay, RC node has strong count of 1 and weak count of 0. In the inner scope, create branch and associate it with leaf. At which point, when we print the counts, the RC node in branch will have strong count of 1 and weak count of 1 if parent pointing to weak. Yeah, so both are 1. 1, 1. When we print the counts in leaf, we'll see it will have a strong count of 2 because branch now has a clone of RC node. Where's branch? Branch strong. That's the answer for branch strong. What's the answer in quote? Branch strong 1, weak 1. Branch strong 1, weak 1. Branch strong 1, weak 1. Weak 1 because it's downgraded. Okay, about leaf strong. Strong leaf. What do we have here? This is 1, 2. Is it 2? Branch strong, leaf strong 2. Weak count, leaf weak 1. Is it correct? 2, 1. Oh, it's 2, 0. Which one is 0? Is it 0? In branch will have a strong count of 1 and a weak count of 1. Branch. Strong count of 1, so the clone, and a weak count of 1. So the leaf parent. For leaf parent pointing to branch with a weak node. When we print the counts in leaf, we see we still have a strong count of 2 because branch now is a clone of RC node. If leaf stored in branch children, RC node of leaf stored in branch children, but will still have a weak count of 0. Because branch now has a clone of RC node. Branch has a clone of RC node. Has a clone of leaf stored in branch children, but will still have a weak count of 0. Of leaf stored in branch children, but will still have a weak count of 0. Leaf strong 2, weak equals 0. Where is it? Leaf strong 2, weak count is 0. Let's analyze this. Strong count 2 because branch is doing this RC clone to leaf. This is 1 here. Whereas RC clone. Leaf strong equals to 2, weak equals to 0. Weak counting, okay, so it's counting leaf. Was leaf downgraded somewhere? Oh, the downgrade is only here. So this one is actually okay, from branch. No, this is leaf. Leaf parent. Leaf parent. Okay, there's a new to a weak. New. Leaf parent. Borrow upgrade. Okay, so in this case, because of upgrade will return weak. So leaf parent none. Leaf strong 1. 1 for strong. Strong count. Okay. Strong. Leaf strong becomes 1. Leaf strong becomes. How is strong? See, because of parent that was upgraded. Then weak. Okay, here weak is already 0. That one is confusing. It's confusing. What can we get from here? Okay. When the inner scope ends, branch goes out of scope and the strong count for RC node decreases to 0. So its node is dropped. The weak count of 1 from leaf parent has no bearing on whether or not node is dropped. So we don't get any memory leaks. If we try to access the parent of leaf, after the end of the scope, we'll get none again. The end of the program, the RC node in leaf has a strong. Okay, so if you get RC node, then leaf has a strong count of 1 and weak count of 0. Because the variable leaf is now only reference to RC node again. All of the logic that manages the counts and value dropping is built into RC and weak. Their implementations of drop trade, specifying that the relationship from children to its parent should be weak. The reference in the definition of node will be able to have parent nodes pointing to child nodes and vice versa without creating a reference cycle and memory leak. Summary. In this chapter, we have covered how to use smart pointers to make different guarantees and trade-offs from those Rust makes by default with regular references. Yeah, so we started with box T, which has a known size and points to data located on the heap. The RC type keeps track of the number of references to data on the heap so that data can have multiple owners. The ref cell type with its interior mutability gives us a type that we can use when we need an immutable type, but we need to change an inner value type. It also enforces the borrowing rules at runtime instead of at compile time. Also discuss where the deref and drop traits, which enable a lot of functionality of smart pointers. We explored reference cycles can cause memory leaks. and how to prevent them. To prevent them is using weak T. If this chapter has piqued your interest and you want to implement your own smart pointers, check out Rustonomicon. I think this is the dark rust, the dark arts. Yeah, the dark arts. Okay, we don't want to touch on that yet. We want our code to be safe. If this chapter has, okay, more useful information. Next, we talk about concurrency. Woohoo! It's interesting topic. You'll even learn about a few new smart pointers. So, let's start. What's in Fearless Concurrency? Handling concurrent programming safely and efficiently is another of Rust's major goals. Concurrent programming, in which different parts of the program execute independently, and parallel programming, in which different parts of the program execute at the same time, are becoming increasingly important as more computers take advantage of their multiple processors. Historically, programming in this context has been difficult and error-prone. Rust hopes to change that. Initially, Rust's team thought that ensuring memory safety and preventing concurrency problems were two separate challenges to be solved with different methods. Over time, the team discovered that the ownership and type systems are a powerful set of tools to help manage memory safety and concurrency problems. By leveraging ownership and type checking, many concurrency errors are compile time errors in Rust rather than runtime errors. Therefore, rather than making you spend lots of time trying to reproduce exactly the same circumstances under which a runtime concurrency bug occurs, incorrect code will refuse to compile and present an error explaining the problem. As a result, you can fix your code while you're working on it rather than potentially after it has been shipped to production. Yep, so this is a very important point here. Fix the code while working on it because it will not compile rather than potentially after it has been shipped to production. We've nicknamed this aspect of Rust Fearless Concurrency. Fearless Concurrency allows you to write code that is free of subtle bugs and is easy to refactor without introducing new bugs. Okay, Fearless Concurrency. Free of subtle bugs. Okay, note, for simplicity's sake, we refer to many of the problems as concurrent, rather than being more precise by saying concurrent or parallel. For this chapter, please mentally substitute concurrent and or parallel whenever we use concurrent. In the next chapter, where the distinction matters more, will be more specific. Okay, many languages are dogmatic about the solutions they offer for handling concurrent problems. For example, Erlang has elegant functionality for message passing concurrency, and has only obscure ways to share state between threads. Supporting only a subset of possible solutions is reasonable strategy for high-level languages, because higher-level language promises benefits from giving up some control to gain abstractions. However, low-level languages are expected to provide the solution with best performance in any given situation and have fewer abstractions over hardware. Therefore, Rust offers a variety of tools for modeling problems in whatever way is appropriate for your situation and requirements. Here are the topics you'll cover in this chapter. How to create threads to run multiple pieces of code at the same time. Message passing concurrency, where channels send messages between threads. Shared state concurrency, where multiple threads have access to the same piece of data. The sync and send traits, which extends Rust concurrency guarantees to user-defined types as well as types provided by the standard library. So forming points, how to create threads, message passing concurrency, shared state. Okay, there are two ways of doing it: message passing concurrency and shared state concurrency. Multiple threads have access to the same piece of data. Channels and messages between threads. And then finally, sync and send traits. So these are traits you can implement for a threading or concurrency. Let's see. Using threads to run code simultaneously. In most current operating systems, an executed program code is run in a process, and the operating system will manage multiple processes at once. Within a program, you can also have independent parts that run simultaneously. The features that run these independent parts are called threads. For example, a web server could have multiple threads so that it can respond to more than one request at the same time. Splitting the computation in your program into multiple threads to run multiple tasks at the same time can improve performance, but it also adds complexity. Because threads can run simultaneously, there's no inherent guarantee about the order in which parts your code on different threads will run. This can lead to problems such as race conditions in which threads are accessing data or resources in an inconsistent order, deadlocks in which two threads are waiting for each other, preventing both threads from continuing, bugs that happen only in certain situations and are hard to reproduce and fix reliably. So I think these are three main culprits in threads. Race condition, deadlocks, and bugs that are hard to reproduce in certain situations and are hard to reproduce and fix reliably. Rust attempts to mitigate the negative effects of using threads, but programming in a multi-threaded context still takes careful thought and requires a code structure that is different from that in programs running in a single thread. Programming languages implement threads in few different ways, and many operating systems provide an API the language can call for creating new threads. The Rust standard library uses one-to-one model of thread implementation, whereby a program uses one operating system thread per one language thread. There are crates that implement other models of threading that make different trade-offs to the one-to-one model. Rust async system, which we will see in the next chapter, provides another approach to concurrency as well. Okay, creating a new thread with spawn. Maybe let's create a new project for thread. Maybe we can name it as Fearless Concurrency. New Fearless Concurrency. Okay, so it compiles. Save that one. Back here. Let's copy everything. Okay, what we have here. Creating a new thread to print one thing while the main thread prints something else. Note that when the main thread of a Rust program completes, all spawn threads are shut down. Okay, very important. Main thread of Rust program completes, all spawn threads are shut down. Whether or not they have finished running. The output for this program may be a little different every time, but will look similar to the following. There's the main thread here. Main thread. I don't know which one is the main thread. Maybe main is the main thread. Then thread spawn is the thread created here. Yeah. So it says here if you run this, you might not get the same result. 1, 1, 2, 2, 3, 3, 4, 4, 5. But for us, is it in proper order? 1, 1, 2, 2, 3, 3, 4, 4. Oh, we don't have 5. We don't have 5. Okay. The calls to thread sleep forces a thread to stop its execution for a short duration, allowing a different thread to run. Force the thread to stop its execution for a short duration, allowing different thread to run. Where is it? Sleep. Sleep is here. Sleep is also here. The threads will probably take turns, but that isn't guaranteed. It depends on how your operating system schedules the threads in this run. The main thread printed first even though the print statement on the spawn thread appears first in the code. Even though we told the spawn thread to print 1 to I until I is 9, it only got to 5 before the main thread shut down. If you run this code and only see output from the main thread, you don't see any overlap, try increasing the numbers in the ranges to create more opportunities for the operating system to switch between the threads. What is there in the ranges? Here? I number blank from spawn thread. It doesn't get to 10. It's only up to 5. Oh, main thread. Okay. Now I understand a little bit. So main thread is this one. Thread that sleep duration. That's why you have this statement here. High number blank from main thread. High number 1 from main thread. High number 1 from spawn thread. So this is main spawn. So it means that after for loop, thread is already done. And then the spawn thread, okay, let's take a look. Number 1 from main thread. So this is executed 1. Number 1 from spawn thread. Okay, so 1. Number 2 from main thread. 2 from spawn thread. 3 from main thread. 3 from spawn thread. 4 from main thread. 4 from spawn thread. 5 from spawn thread. So it stopped. Okay. Before it only got to 5 before the main thread shut down. Yeah. Okay. Does it mean that because here it's 1 to 5? 1 to 5, after 5, the main thread already shut down. So this one cannot continue from 1 to 10. If you run this code, only see the output from the main thread and don't see any overlap. Try increasing the numbers in the ranges to create more opportunities for operating system to switch between threads. Ranges here. So if we change this to 10, then probably we'll get more numbers. Let's see. Okay, run this. Yeah, so 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9. Because we have increased this. Waiting for all threads to finish using join handles. Okay. The code listing in 16-1 not only stops the spawn thread prematurely most of the time due to the main thread ending, but because there is no guarantee on the order in which threads run. You also can't guarantee that the spawn thread will get to run at all. You can fix this problem of the spawn thread not running or ending prematurely by saving. Okay. So here we can see if it's 10, there's opportunity for the spawn thread to run. Put 3. Spawn thread 1, spawn thread 2. Main thread 1, main thread 2. Let's run it. So this time it's only up to 2. Main thread 1, main thread 2. So by only having 2 main threads, the spawn thread was able to generate 3. Interesting. Okay. Here it was changed. Where you have calling join on the handle blocks the thread currently running until the thread represented by the handle terminates. This handle. Here. Handle thread spawn. We'll change this one and put this in. Handle join unwrap. So the thread that was spawned going to wait for it. Okay. Calling join on the handle blocks the thread currently running until the thread represented by the handle terminates. Handle, this one. So it is the spawn threads. Spawn threads are being joined to the main thread. Blocking a thread means that the thread is prevented from performing work or existing. because we put the call to join after the main thread's for loop, running the string 16-2 should produce output similar. Points to handle. Okay, so does it mean number 1 from main, 2 from main, then number 1 from spawn, main is already 3, spawn 2, 2, 2, from main thread 4, okay, from spawn thread 3, 4, 5, 6, 7, 8, 9. Let's see the output. It's 1 to 10, 1 to 5. Let's change this to 5. Run. Oh, we have more things here. Main thread, then 1 from spawn thread, 2 from main, 2 from spawn thread, 3 for main, 3 for spawn thread, 4 for main, 4 from spawn thread, 4, 5, 6, 7, 8, 9. What does it mean? From the spawn thread. Here. So before everything terminates, it seems like the handle got to until 9. Yeah. So even if we run this multiple times, 2 seconds, the spawn thread will always be to 9. Okay, let's analyze this one. Handle join does not end until the spawn thread is finished. But let's see what happens when we instead move handle join before the for loop in main. For the for loop in main. I think this one, once it reaches to 9, that one will stop. Will stop printing. It's placed in between the for loop. Okay. Okay, then the handle below, we comment it out. So if we run, it will wait for 1 to 10 or 0 to 9 to execute. They will join together. Mm. 1 to 9. The number 1 from the main thread. Okay. So it shows like you split up the task having 9 threads, but you're waiting for them to join here and then you proceed with this one. Yeah. Small details such as where join is called can affect whether or not your threads run at the same time. Let's try running it again and see what happens. 1, 2, 3, 4 for main thread. Yeah, this one only happened after this finish executing. Using move closures with threads. I think let's end here for now. And we'll continue with this topic tomorrow or the next day. So we'll go through this part first, using threads to run code simultaneously, and then creating a new thread with spawn, waiting for all threads to finish using join handles as a review, and then we continue with this. All right, so thank you so much for accompanying me today. This is an interesting topic. We have reached day 26, touching on fearless concurrency. So congrats to everyone. We have made it quite far, I would say. Yeah. Counting on the days officially, yeah, of course, 26 days for me. Not sure how many days, but it doesn't matter. As long as we keep on pushing forward, hopefully we can finish the Rust book. Thank you so much. Let me thank my supporters as well.